Okay, I'm here with the part 2 of the video. My Apple Pencil stopped working, so I had to get that fixed. So we're just going to finish off the rest of the questions now. Okay, we ended up stopping here where we had a triple bond, and in the ending the two BRs were trans to each other. We learned that if you have a trans double bond, that's going to hold true. If you want them to be on the same, well, we had a question just like this before, and that was right over here. See, if we had a cis double bond, you end up making both of the things go same, just like that. So we know that I have to make a cis double bond out of a triple bond. So I know right before this, it looked like this. So the question is, how do you make a cis double bond? Starting with a triple bond. And that reaction is H2 over Lin-Lar's catalyst. How do you make a double bond go to 2 BRs? Well, that's just Br2 over CH2Cl2. I know this is gonna form something like this, a wedged and a dash Br, like that. But when I rotate around the single bond, I'll make my correct answer. So if you want to write it all on the line, you just go 1 and 2. You go first step, I make H2 over Lin-Lar. Step 2, you do Br2 over CH2Cl2. Awesome. Next reaction is a chapter 11 reaction. This reaction is you have to go... I went over this reaction already. It was H2 over PT or PD. And all that's doing is it's adding two H's. So in this case, I would end up adding an H on both of the spots for the double bond. Now notice those H's have to go cis to each other. So let's say if they did go cis to each other, well then these both things will be wedged like that. Okay, you add two H's that are cis to each other. It's a syn addition. In this case, I think I form, let's see, 1, 2, 3, that's a S. This one is a 1, 2, 3. This one is a S also. Since I'm forming SS, it totally does matter. The other answer would be if these parts came in as a dashed and my H's came in as a wedged, like that. So if it was a meso compound, it wouldn't matter, but in this case, the R and S matters because we ended up making an enantiomer. So it would be these two answers right there. Okay, next reaction is how you form an NH2. Now, I thought of two ways of doing this, although I think one way is a little bit faulted. I think the official way that she maybe wants you to do it is to make an NH2, you have to first have a N3. One important thing to note here is that in the beginning I have 3 carbons and at the end I have 3 carbons. So I can't possibly add any carbons. So if you have that, then before NH2 looked like N3 and all we did was H2PT or PD. Right? Or PD, whichever one you want. So the question is, how do you make N3? Well, N3 was taught using SN2. So we can just do NaN3 over DMSO. Now the question is, well, how do you get a Br? Well, that's starting with the alcohol at least. Well, that's just PBr3 over, I believe, heat. I think there was also PY. So if you want to put it all together, you just go 1, 2, and 3. So you go step 1, well, I do PBr3 over PY in heat. Step 2, I go NaN3 over DMSO or DMF, whatever. And step 3 is H2PT or PD. Now in this one, I started with 3 carbons and I ended up with 4 carbons. The only way that's possible, and also I made that NH2, the only way that's possible is if before this looked like a CN. So look, if there was a C triple bond N here, well, that's my extra carbon. So the question is, how do you turn a Br into CN? That was also last exam, which was just NaCN over DMSO. It's a SN2 reaction. And then to turn a CN into NH2, you again do H2PT. So writing it all in one step, that's NaCN over DMSO. And part 2 is H2 over PT. Next reaction. This reaction specifically, also chapter 11 reaction. Now, I think this says Fe. I couldn't exactly read it, but this is actually a reduction reaction. Um, and it's very specific. It just turns NO2s into NH2s. It's very specific to the benzene, so I don't know the likelihood of this being asked. Okay, next question is we have an aldehyde. Now, normally we learned this using a triple bond. We said if you have a triple bond, you can make an aldehyde with BHCl2. So if you want to, you can turn this into a triple bond at the end and then go that. That's possible, but that's not testing new concept we learned in chapter 11. So the new way to do it would be, well, we can make an aldehyde using an alcohol. Alcohols can oxidize into aldehydes. And in chapter 11, you'll learn multiple reactions that do this. In fact, there's, I believe, 3 reactions that will do this. We will be always using PCC over CH2Cl2. Now, if you've read chapter 11, you'll understand this. If you don't, I will go over it in next class. But I do know that I need alcohol at the end. Wherever I have the aldehyde, that's the spot I need the alcohol on. So how do you get an alcohol starting with this double bond? Well, I know this double bond's over here, so I put the OH at the end. The way you do that is BH3, it's hydroboration, THF, the H2O2, NaOH, water, all of that. Water, step 2 and step 1. So write it all in one step right here. I'm not going to rewrite it. In this one, again, like before, we're going to do PCC, just like before, PCC over CH2Cl2. But now I need the alcohol on that exact spot. How do you get that from a double bond? Well, that's just H2SO4 with water. So I feel like these questions are like mini synthesis. So I would write it as 1 and 2 over here again. In this one, I have a carboxylic acid. And it turns out to make carboxylic acids from a alcohol, that requires a strong oxidizer. Also, chapter 11, we'll go over it in the next class, but if you want the answer, it would be H2Cr2O7. I believe it's over H2SO4. Anything with a Cr is a strong oxidizer, and it makes alcohols go all the way to the end, which is a carboxylic acid. Something like a PCC is a weak oxidizer, and it only makes it go to ketones and aldehydes. Question is, how do I get the alcohol at the end? Well, that's just the same thing as before right here. We're going to do BH3, THF, all that. BH3, THF, step 1. Step 2, H2O2, NaOH, and water. There you go. So write it all here. MnO2 is a very specific reaction again. I will go over it. If you ever have a alcohol that's at the benzylic or allylic spot, that is when you can do this reaction. So notice this carbon right here, or this alcohol, that's right next to a benzene. So it only affects those spots. That's it. If you have an alcohol next to a benzene like that, that's when this reaction is going to happen. And all you're doing is you're oxidizing that part. So this alcohol is untouched. It's not at the benzylic spot, so it doesn't matter. But this alcohol is going to get turned into a double bond O, like that. Your answer should be what I just drew. Right there. You look for allylic and benzylic alcohols, and they get oxidized. This reaction is actually called Swern oxidation. It's same as PCC. PCC is easier to write, so we're just going to keep using PCC. But if they give you these reagents, you know that's just PCC. Again, I will go over it in chapter 11, but if you want to know the answer, you're going to oxidize both of the spots. But it's still a mild oxidizer, so we're going to end up making a aldehyde out of that and a ketone out of this. Next reaction is OSO4. This reaction, I believe I went over with some of the students, but not everyone, because I figured out it was a chapter 11 reaction. This reaction adds 2 OHs, and it's a syn addition. So, on both spots, I need to add the H's cis to each other. So, I can make them go dash to each other like that. In this case, I would get a 1, 2, 3 S on this spot. 1, 2, 3. Wait, I'm sorry. I think it's 1, 2. Yeah, it is S over here. Here it's 1, 2, 3 R. So this is actually a meso compound. If you can't figure that out, you're going to have to practice some of that R and S, and you got to know that for the final anyway. So I think this is right. If I made a mistake, let me know in class. Next one. Okay. This one you're adding a OH and a BR, but for some reason there's a methyl missing here. I think she wanted to write a methyl there. I think she messed up. But notice that the OH and the BR are trans to each other. Well, that makes sense. And this reaction would just be Br2 over water. There's no way that this methyl right here just disappeared. So I think she wanted the methyl to be there. Okay, in this reaction, again, it's a bit odd. Let me think about it. We do have 3 carbons in the beginning, and then we're going to 4 carbons. You haven't learned that, so I think this is supposed to be only 3 carbons long. I don't know if I made a mistake. Let me check, actually. Give me 1 second. Let me check. Number 36. Yeah, she did draw it as 4 carbons. I think she might have meant 3 carbons only. That would make more sense. I'm not sure, but if it is 3 carbons, this is actually a reduction step. And for reduction, you guys are going to learn NaBH4. That should be the reagents. It's in chapter 11. Okay, next one, we're going from a ketone to a double bond. Well, I know to form double bonds, I have to do some kind of elimination, and elimination generally requires you to have either alcohols or BRs and CLs. So I know if it's alcohol, I can do elimination from last exam with H2SO4, water, and heat. And it turns out you can make alcohols with ketones because it's just reduction. This is again just like before, it's reduction. And the reagents would be NaBH4. Now I am pretty sure there's more stuff to that. It's in chapter 11 for the exact reagents, but it's the one with NaBH4. Next one is DMP. Okay, this is the last reaction that's a mild oxidizer. So there were 3. You can either write this, DMP, or you can write PCC, CH2Cl2. And the last one was the DMSO, this thing. So that's right here, COCl2. Or that's not COCl2. So here, let's write here, COCl2 over NET3, triethylamine. So all 3 of these do exactly the same thing, and they just oxidize an alcohol. In our case, our final answer will be the benzene doesn't get affected. Only the alcohol gets turned into a ketone, like that. HiO4 is very similar to ozonolysis. For the students, I actually taught this. Remember, let's do question number 40 first. The way I taught this was kind of just make a line through the double bond, and we can just put oxygens on each side. So if I was doing this question, we would kind of just go make this again. Here, we can make this part a little bit longer. You can just go make this again. And all you're doing is you're making a line towards the middle, and then you're putting oxygen on both sides like that. Those should be your 2 answers. This happens to be an aldehyde like that. Now, if the second part is CH2S or DMS, dimethyl sulfide, then this stays as a H. The aldehydes is going to stay as a H. You're going to make an aldehyde indeed. But if you have the second step as a H2O2, then the same reaction occurs, except the aldehydes won't be aldehydes actually, they'll be carboxylic acids. So that's the only thing that changes. With HiO4, it's very similar to ozonolysis, and I want you to think of it like this. This is not exactly how it works, but it'll help us not mess up. So find the spot where the two OHs are right next to each other. Imagine if there was a double bond there, right? So imagine it looked like this. Okay. After this, all you're doing is ozonolysis. So if we just do ozonolysis here, well, I would get this, right? You would go erase the middle and add your O's like that, right? So that's all you're making. That would be your answer. HiO4. Again, this is not really how it works. You don't really form that double bond. It's just, I think it's easier for the students to see. It's also a ring opening or opening reaction. It just breaks everything in half. Okay, next reaction. Okay, as of right now, this is not a reaction. I think she just missed a double bond there. If you do add the double bond there, then it becomes a Diels-Aldrich reaction. So if it's a Diels-Aldrich reaction, we first have to make this go as cis to each other. You can do that by making that little mirror thing we learned. The methyls up top, and then this is my dienophile. Okay. The next thing is you figure out who you're listening to. Well, I'm listening to that and that. If I'm listening to that, I should get partial negative on the bottom, partial positive on top. And if I'm listening to this guy, I should get partial positive on bottom, partial negative on top. The negatives are matching up, and once they match up, you make your little cyclohexene. This is pointing out, so it goes dashed. This is the one I listen to, so it goes dashed. There you go. That would be my answer. Next one, this is again a Diels-Aldrich. Now, this part is a cyclic, so I know I make a bicyclo structure. So already I can start with this. I make my double bond here, and I make this little bicyclo structure like that. These are considered to be pointing in. Because they're pointing in, they have to go wedged. Now, I don't want to make this look ugly and make that part wedged, so we're just going to make a dashed H here. Again, these are two spots. And then the other part is a triple bond. So if I wanted to make it look better, I can make it like this. This is essentially what we have. So the second part would be a double bond with a ketone on it like that. Since I had a triple bond, this is still sp2, so the wedged and the dash doesn't matter. This would be your answer. Next one, again, I have a cyclic structure, so I should make a bicyclo. In this case, I will end up making this one right here. Just like before, this is considered pointing in, so there's dashed H's here. Here, let's just say we listen to one of them. Let's say the top one, well, then that one's going to go dashed. And then the other one is trans to it, so that one has to go wedged. That would be my final answer. I'm just going to move that answer over here. There you go. Next one, again, another Diels-Aldrich question. Let's make the mirror image here again. So the mirror image would look like this. Both of the things are pointing out. So you have a OCH3. I'm going to erase this. So both of the things are pointing out. We have OCH3 and a methyl pointing out, and then your dienophile looks something like this. If we do the things that we're listening to, while we're listening to that and that, you get a partial negative here, partial positive here, partial positive here, partial negative here. Everything is matching up at this point. I can make my answer. This and this is pointing out, so they both go in as dashed. This is the one I listen to, so that goes dashed. The other one is trans to it, so that one goes wedged. Just like we learned in class. That would be my answer. Next one is asking me for what two things make this answer. Now again, I think the question is faulted again. There should be a double bond and... Oh no, this is actually not faulted. Wow, I just thought about it. Okay, so this is again a Diels-Aldrich reaction, especially because we have A and B here. So because the double bond is here, you can think of it like this. This part, 1, 2, 3, 4, is your diene, and this is your dienophile because the double bond gets made there. So this is a little twisty, that's why it looks weird, but essentially the answer would be this is your dying. I'm going to make that in red. This was the dying. There, that's the red circles. And then the dienophile, they both cis, so they both have to be in the same spots like this. Those would be the two things that make that answer. Wow, that was a good one. Okay, next question. Now we're thinking cop dot. Okay, but notice I'm starting with a cyclic structure and I'm ending with a cyclic structure. The only way that's possible is if I open the structure up and then I closed it again. So it should go 1 and 2, and then maybe first one is heat or light. I don't know yet. And then the second one's also going to be heat or light. Okay, so we have to figure out what it is. All right, let's try to figure it out. Now, here in the beginning, I'm starting with a cyclic structure, so let's work vertically. One thing is pointing up, the other is pointing down. I know I have, I know. Okay, so let's just work out both methods. So let's see what this would look like if I go conoratory. So this is conoratory, and then we'll also see what happens if it's disrotatory. If it's conoratory, and imagine if I move this one clockwise, well then it'll end up looking like this. And all right, let's actually let me draw it like this. This will be easier to see. Let's make this one go down, this one go up. So if I go clockwise on this, I'll end up with this. If I go clockwise on that, I'll end up with that. They should be pointing away from each other at the end. Okay. If I go disrotatory, which is right here, so again pointing in and out. Let's say I go disrotatory. Well, then let's go clockwise on this one. Clockwise on that. That one will end up giving me that. And counterclockwise on this one will end up giving me that. So I have two possible options. I know if I go conoratory way, then I'll end up having the middle thing facing out each. If I do the other one, I get them facing in the same way. Technically, we can do either one. It really doesn't matter. So let's say we do the top one. Okay, so if I do the top one, I know it's conoratory. So C, and then my thing is even. So that would be set. So the top one happened in heat. The bottom one is D, so D even. That one was in photo. So if I did the bottom one, I would have to write photo. Let's say we did actually do thermal. I know if I did thermal, that would be the top option, and my middle thing would look something like this. Okay, now I want this to go to this. Okay, I want them to face the same way at the end. So you say, okay, well, if they were facing the opposite ways in the beginning, how can I make them face the same way? Well, I know if I go counterclockwise on this and clockwise on this, they would face the same way. So I just want this to go disrotatory. How do I make it go disrotatory when it's even? Well, that's dep. I have to put it in photo. So second step has to be light. Now, if you do it the other way, where if you did light first, then heat, that would also be the answer. If you have questions about this, if this is too weird, I'll go over it in class again. It's kind of confusing because she put two questions in one. All right, I'm going to move on. Next question is also cop dot. We're working backwards again. In the beginning, I look like this, opposite to each other. This is thermo. This is considered odd because circle counts as one. So that's dot. I know I have to go disrotatory. So let's make this one go clockwise. Well, that looks like this. And if I make this one go counterclockwise, it'll look like that. The final answer should be here. I'm going to just erase this. The final answer should be this. Same way. Done. Next one. Right now, my thing does not look like S-cis, so let's make it go S-cis. Well, that would give me that. So if I redraw that, I get this. This, and that. Just like that. And then we're working at the same thing. I have even. I have photo, so this is dep. I have to go disrotatory. In the beginning, they're pointing away from each other. So if I go clockwise on the right one, I will get this. If I go counterclockwise on this one, I would get this. In the end, they have to point the same way. If they have to point the same way, my final answer would look like this. Final answer. Sorry, it makes the cyclobutane. Final answer would be same way. So both wedged or both dashed. Doesn't matter. Alright, next reaction is a Diels-Alders. I'm beginning with a cyclic structure. So I know I should make a bicyclo like this. Just like that. Again, this is the thing pointing in, so we're going to have dashed H's here again. And then the CL was the one I'm listening to, so we make the CL go dashed. The partial positive and negative, again, doesn't matter because the cyclic structure didn't have any. Okay, at this point, they want us to do KOH, water, and heat. I'm seeing heat, and I'm seeing OH minus, so this is making me think of elimination. Elimination works if you have a leaving group, and my leaving group is the Cl, so I believe the final answer would be to do elimination right there to make this final answer. This is kind of tricky. I feel like these questions are getting tricky as we get to the end. So if you're not getting some of the end ones, it's okay, I guess. This question is definitely not drawn right. It should have been drawn, I believe, like that. The reason why I say that is because this is supposed to be cope, and this should be 1, 2, 3, 4, 5 away. So I think she drew it wrong. Assuming this is cope, and that's actually what she wanted, we just go in a circle. We go this way, like that. This goes here, and this forms a ring. So if I redraw that and I erase and I go, that will look like this. So we erase this bond and make a bond here. We're erasing this bond and making a bond here. Wow, this looks really ugly. Let me fix that up. And then the last bond was we erase this bond and make a bond here. So this is making a 1, 2, 3, 4, 5, 6, 7. A 7-atom ring. Those are hard to make. With the ethyl, a double bond, and then 1. Wow, that's a really weird answer. It looks something like that. That looks really weird. But this is what we have. 7, 1, 2, 3, 4, 5, 6. So this is drawn right. That looks really weird. That's a confusing question. So that was cope. Next one is Claisen. I'm going to redraw this over here. So first, again, we have to redraw this so that it's in like a little cyclic structure like that. At this point, you can go in either direction. Let's say this. If you do that, you'll end up making, we'll copy this question. So let's say we copy this, paste it here. We're going to erase and we go. So we erase this bond and it formed a bond right there. Then we erase this bond to form a bond over here. And lastly, we erase this bond to form a bond over here. Now, whenever there's a benzene involved, I said during the pre-mock that you can't leave it like this. Even though the ketone, like the ketone to the enol thing, the enol wasn't stable, it is stable if you can reform the benzene. So we don't end the answer like this. You have to reform the benzene, making it look like this. And then this just turns into an alcohol, just like that. So a mini ketone to enol happens there. This would be our final answer for number 52. Last reaction, or last question, is cope. So again, you're going to have to redraw this. I always say to first get it into this little mode. Call this 1, 2, 3, 4, 5, 6. Actually, it's easier if we do it the other way around. So let's say we number this. We say 1, 2, 3, 4, 5, 6, 7, right? I don't know which way would be easier. Okay, we're gonna go with the first way. I think the first way might be easier. So if we say this is 1, 2, 3, 4, 5, and 6, then this would be 1, 2, 3, 4, 5, and 6. Okay, so on 1 there's nothing, 2 there's nothing, 3 there's nothing, 4 is where there's the 2 CNs. 5 has a methyl and the double bond, and 6 has a methyl also, like that. Okay, we can erase our numbers because they're annoying. At this point, you can do your go around like that. And we're just going to erase and go. So if I copy this question again, paste it here, let's just erase and go. So we go, this bond gets erased and goes over here. This bond gets erased and goes over here. And then this bond gets erased and goes over here. Those are my 3 things. If I want to make this look a little bit better, we can draw our CNs a little bit better, like that. So something along those lines, if you want to make that part look up, something along those lines. And I think that was the last question. So yeah, I did get kind of crazy near the end. So I hope you got some of those. Now I'm only a human. I could have made like mistakes here. Again, this is just me doing them live. So I didn't really know this. I had to write them out. So as I was writing them out, I was kind of thinking about them. But yeah, I think it was okay. It got kind of hard at the end, but if you have any questions about them, you can definitely ask me during the practice problem sessions or after class, before class, assuming I'm in class early. Use this as a guide, or to make sure that you got the answers right, or you have your thought process right. And yeah, your exam's coming close, so I hope you guys are ready for the test. I'll see you guys during next class. Good luck.